In this video, I'll be looking at the equilibrium of forces. That is, by extension, the equilibrium of bodies at rest under the action of some forces that are balanced. And it's a topic under mechanics. And mechanics is the study of the forces that act on the body. Of course, we know that we have three other branches of mechanics. We have the solid or rigid body mechanics, we have the deformable body mechanics, and we have the fluid mechanics. When we talk about the deformable body mechanics, we speak in terms of the behavior of materials when compressible forces, forces are applied to them. And then we talked about the fluid mechanics, that is the behavior of fluid under balanced and unbalanced forces. And of course, under that, you can also subdivide that into compressible fluid mechanics and incompressible fluid mechanics. Then under rigid body mechanics, we have the statics and the dynamics. Statics, that's the topic we are looking at this time around. I've already explained static and dynamic equilibrium. And I said for static equilibrium, this body is in the state of rest under the action of the number of forces acting on it. And this body has no motion in itself. It doesn't move. It's just in a state of perfect rest. And for dynamic equilibrium, the body is not at rest per se. It's in motion, but the forces stay cancelled out. In that case, so the body moves with a constant speed. That's the case of dynamic equilibrium. And then here we're going to look at that and also see the difference, the distinction between resultant and equilibrant forces. Then we'll see the equilibrium of two forces, and if I have all the time, the equilibrium of three forces. Now, for resultant force, let's see what do you mean by, what do you understand by the concept of resultant force? We see it is that single force that has the same effect both in magnitude and direction as the two other forces acting together. That is equilibrium of two forces. Okay, the way means that let's say we have two forces, for instance, and these two forces are acting. Let's say they act in this way. This force P and this is force Q. We can find their resultant. If the system or the object here at point O is not at rest, it means that there's a resultant of a resultant force that act on it. And that resultant can be found using, I've told you different methods in my previous video. I've explained how we can use triangle method to find the resultant of two forces, parallelogram law of vectors to look at the resultant of two forces, or to resolve or to find or determine the resultant of two forces, and then the calculation method, that is using the cosine formula to find the resultant of two forces. Okay, so the resultant, if we use the parallelogram law of vector, maybe by scale drawing method, I need to complete this to make it up to a parallelogram. And then I have this as my parallelogram, meaning that this side is equal to and parallel to Q. The vector Q acts along this line, and this line too represents vector P equal to and parallel to this. So the diagonal of this parallelogram drawn from the common point of action, the diagonal is the resultant vector. Okay, and that resultant vector has the same effect as these two vectors. The resultant vector can replace these two vectors. It has both, in terms of magnitude and direction, is the same as vector P and Q acting together. Now, it means that if this system, this body here was to move, it will move along this line. The direction is this direction of the resultant vector, the angle it makes with the x-axis. Let's say that Q is acting along the x-axis. So if I must bring this system under equilibrium, I need to introduce the equilibrium force. The equilibrium force we have the same magnitude as the resultant force, but must act in opposite direction. So that gives the difference between the resultant force of these two forces acting at point O and the equilibrium force. That is, in terms of magnitude, the equilibrium force must be equal to the resultant force R. So if the resultant force was 5 Newton, for instance, it means that the resultant force will also be 5 Newton. I mean, if the resultant force was 5 Newton, the equilibrium force will also be 5 Newton. And then in terms of direction, the equilibrium force E must be equal to, or let's say, act in a direction opposite. So I'm going to introduce negative sign to show that it's acting in a direction opposite to the direction of the resultant force. So That's it. So, which means the resultant force, let's say resultant of two forces, is that a single force that has the same effect both in magnitude and direction as the two forces acting together, while the equilibrium force is that single force that has the same magnitude as the resultant force, but acts in a direction that is opposite to it. All right, so quickly let's look at the equilibrium of two forces. When two forces are said to be in equilibrium, it means that number one, the two forces must be equal in magnitude. That's number one. And then number two, they must act in opposite direction. Equilibrium of two forces. Okay. All right. So let's say we have case one. You have a case of an object that is just at rest on a surface, a smooth horizontal surface, so to speak. Let's say I have this block or this block of mass. Now the weight of this block of mass acts vertically downwards. We all know from the concept of weight that it has a direction, it's a vector quantity. So the direction is always vertically downwards. So that's the weight of this body. And then how do you calculate the weight of a body? It is defined as a product of the mass of the body and acceleration due to gravity. So if I'm on the earth surface, g is roughly 10 meters per second squared. I multiply that by the mass of the body in kilogram. That gives me the weight of the body. Now that's this weight of this body is acting downwards and is pressing down on the table. So there's going to be a kind of reaction. We call that normal force acting from the surface of the table, and this normal force acting in a direction at right angles to the surface of the table, the horizontal surface. Okay, this normal force N, acts in this direction upward. Now, for this book or block of mass to be at rest on this table, it means that number one, the two forces must be equal. That is, the weight of the body must equal the normal force. Some call it normal reaction, normal force N or normal reaction. That is one. And the two forces must act in opposite direction. That is, the weight must be equal to minus what? This negative shows that the direction of action of these two forces are not equal. One is opposite in action to the other one. Okay, so that's the direction. We can also apply this to cases like if you have some people they install ceiling fans in their rooms. This ceiling fan is just hanging there in space. It's not falling downwards. It's not accelerating upward. What keeps the fan in the state of equilibrium? Let's say we have a ceiling fan. Let me just show you a picture of it. Let's see that is the base of it, and these are the blades of the ceiling fan. And this ceiling fan is just suspended there, is hanging in space. Let's say it's not rotating. We say it is in a state of equilibrium under the action of two other forces. What are the two forces? The weight of the ceiling fan, W, acting vertically downwards. And then number two, if this is a metallic pole or made of iron, it means that there's a force that will act along this pole. We can call that tension or thereabout. So that is the force that balances, that acts in order to secure or to maintain the weight of this body, to balance the weight W of this fan. What happens if the weight becomes greater than the tension? Of course, we expect this fan to start moving in this direction, downwards. And if the tension in the pole becomes greater than the weight, it means this fan will not be at rest. You come to your home one day, the fan has shifted upward. It has moved into the ceiling or beyond the roof. Okay, so in another case, for it to remain in that state, the tension in the pole, in this support, this attachment must always be equal to the weight of the fan. So that's the equilibrium of two forces. So think about, just look around you. There are objects around you that are in a state of rest under the action of just two forces. And you can identify the two forces, the weight of the body and then the normal force, in the case when the body is just on the surface, horizontal surface on the floor. How about a body that is being hung on the wall? We can talk about the equilibrium of these forces. If you can identify two forces, or a body that is suspended from a point in the ceiling, and is suspended in space, we can always talk about the equilibrium of these forces. Now we quickly look at the equilibrium of three forces. Equilibrium of three forces. Equilibrium of three, not one, two, three. Three forces, not two, not one. And according to Newton's laws of motion, it's not possible for a body to be in equilibrium when it's acted upon by just a single force. A single force will always produce an acceleration. Of course, it's unbalanced. So when we talk about equilibrium, we are talking about a state where the forces balance. It means they must cancel out each other. We are looking at the case again where there is no resultant force that acts on that body. Equilibrium of three forces. Now, in this case, when a system is in the state of equilibrium under the action of three forces, we say that this body or this system can be represented by the adjacent sides of a triangle taken in order. We'll call that the triangle of forces, forces in equilibrium. So let's take that triangle law of forces or triangle of forces in equilibrium. It is when a system comprises the body and the forces that act on that body. A system is under the action of three forces in equilibrium. It means that the three forces can be represented, the three forces can be represented, let me abbreviate because of time and space, in magnitude and direction by the adjacent sides, whatever adjacent, you know that, of a triangle. Of course, you know a triangle has three sides, right? A triangle taken in order. We call this a triangle of forces. When the forces that act on this body, is that the forces, the body, the system is in a state of equilibrium, static equilibrium. So when the force or when the system is under the action of three forces in equilibrium, then these three forces can be represented in magnitude and direction by the adjacent sides of a triangle taken in order. That's triangle law of forces. All right. So how do we exemplify, demonstrate, or illustrate this triangle of forces principle for bodies in equilibrium? Or before then, maybe I'll quickly talk about the condition for this system to be in equilibrium. Number one, the lines of action of these three forces must pass through a point, or they must intersect. The lines of action of the three forces in equilibrium must intersect, or they must pass through a point. The lines must pass through a common point, pass through a point that is common to the three forces, a common point. If that is not the case, then that body cannot be in equilibrium under the action of three forces. Then number two, it's also possible that the moment, in terms of moment, the moment of any of the forces, moment of any of the three forces about that common point must be zero. About the common point must be equal to what? Zero. So then number three, you can also add that the sum of the resolved component of the forces along any one direction must be equal to zero. Okay, there is sum of the resolved forces. Resolved, forces acting along any direction. It could be along the y-axis or y direction, or along the x direction. Along any direction must be equal to zero. That is to say, the forces are going to, and these forces are not parallel. These three forces are not parallel to each other. But when we resolve them, the ones that are resolvable, we resolve it along the x-axis and the y-axis. But when we now solve these resolved components of the forces along the two recognized directions in physics, vertical and horizontal, it must give us zero. If it is not so, then the system is not in equilibrium. Okay, so number one, we say the lines of action of the forces must meet at a point, must intersect. Number three, the moment of any of the forces about the common point also must be zero. That is, moment of the first, second, and third force about the common point where they intersect must be zero. And then the sum of the resolved forces acting along any one direction must be equal to zero. Again, we can also add this condition to it and say that for these three forces, okay, let me just quickly, before I add that third one, let's see, we have this system of forces, acting on the body, and such that the body is in state of equilibrium, okay? I have I have this. Let's use a pendulum bob now. It's a pendulum, you know, suspended by means of this thread that is attached to a point here. Maybe this is the ceiling, and this is the pendulum bob, a metallic object in shape of a bob. This is a string. Now, at this point, when the pendulum bob is at rest, two forces act: the tension in the string T and the weight of the bob mg. All right. So, if a horizontal force H, for instance, is applied by means of a string that is attached to this side of the bob and is used to pull this bob in this direction, so that this bob is now displaced to the right, let's say somehow displaced vertically upward like this, and by means of this horizontal force that is applied to the ball at this side of the ball. Look at the horizontal force H. Now the tension still act along the string. This is the string, this is my T, and I'll still have this ball, mg is the mass or the weight of the bulb. Okay, in this case, let's say it is such that this string now makes angle theta degrees with the vertical. Is my vertical direction. Now this system is in equilibrium. Yes, under the action of three forces. One, two, three. Triangle law of forces says that we can represent these three forces using the adjacent sides of a triangle taken in order. Order means the way and manner the forces are oriented. That should reflect in the triangle. Now, this horizontal force, of course, you see, it is acting horizontally. I will not represent it with a side that is not horizontal. Okay, seeing this is horizontal, if I'm going to represent it or place it in my triangle of forces, I must draw my horizontal line to depict this force H, because this force H is acting horizontally. That's mean of taking in order. Now, the weight of the body, mg, is always acting vertically downward. The weight line on the triangle must be vertically downward. I can decide to use this to show the weight line. Okay, this is my weight line, all right, acting vertically downward. I can call that my mg. Okay, so this side of the triangle is my mg. And you can see that since this is vertically downwards and this is horizontal, the angle between these two directions is always 90 degrees. So this must be my 90 degrees. And then the tension in the string, you can see how it is acting. You can see the orientation and the direction of force T. It's just like I can remove it, detach it from here without twisting it or adjusting it. The way it is, I bring this, my force T, my line T, and place it here to finish up or to close up the triangle, which means my force T must act like this. Now, it will be very wrong for me to represent this triangle otherwise. That is, place H here, or place T here, or place MG here. It's wrong, because that will not be, representing this figure correctly. To represent the figure correctly, the way and manner the forces are acting must reflect on the triangle. Okay, you see, this is my weight line acting vertically downward, and that is it here. The horizontal force H act horizontally, that is it here, and the tension in the string, see how it is acting. And then this my angle theta, let's define it. It's angle between the tension and the vertical. So I place my theta here. Angle between the tension line and the vertical. Okay, so this is complete representation, and this must form a closed triangle. When you are done with your representation, it must form a closed triangle. What do I mean by that? The forces must follow each other. Look at it. Force P is following force H. Force T follows force H. Mg follows force T, and H follows what? Mg. You can see that now. So they follow up. When the forces follow each up like that, that means the forces are represented or they are taken in which they are represented in this. And if it doesn't form the closed triangle, then there is no, the forces are not in equilibrium, because this case is different from something like this. Supposing you represent your whole and you have something like this, you have this, you have this, you have this. Now, this shows that the forces are not in equilibrium. There's a resultant force that is acting. You can see that now. In this case, you can't tell me or prove to me that the forces are in equilibrium, because the directions of action of the forces don't follow each other. That this one follows this, but this one and this one appears to be meeting at this point. It means that the resultant of these three forces also is this force T. Resultant of these two forces is force T. They are not in equilibrium. But when the forces follow each other like this, for this system to be in equilibrium, it means that the resultant of any two is equal and opposite to the third force. So that is the next thing I need to say about three forces in equilibrium. That the resultant of any two of the three forces at an equilibrium, any two of the three forces is equal to and opposite equal to and opposite to the third force. Opposite to the third force. That is to say, if I use my triangle method of adding forces, I'll have force W plus H is equal to minus force T. All right, so that's what I mean in terms of using triangle of forces to add the three forces acting on this system. It means that this sum of these two forces equal to an opposite to a third force. And so if I bring this here, it means that W plus H plus T must be equal to what? 0. That means that this system from this triangle of forces is in a state of equilibrium. Next video, I shall take some time to solve some questions on this equilibrium of forces. Thank you.